Hello, my name is Jim Osterloh. I'm here at the Catalytic Depolymerization pilot plant owned by Panda Holding in Pasco, Washington, mid-October 2000. First thing to discuss is the basic layout of the facility. We're on the mezzanine deck right now, about 20 feet above grade, about 6.5 meters above grade. Feedstock comes from the east through a vacuum transfer line, enters into a reactor. The reactor has hot oil with a catalyst suspended in it. The product fumes go overhead through a separation vessel into a distillation column. Product condensate leaves the distillation column through several taps and gets pumped over to the tank farm. Non-condensable gases get separated and sent either to a turbine generator or to a flare. One of the first changes, major changes, since initial design and construction in 2017 was the method by which solid feedstock is entered into the reactor. The very final stage of that entry is through two rotary airlocks with a nitrogen purge to keep the oxygen out. Previously, we were transferring with a bucket conveyor and a belt conveyor, discharging into these rotary airlocks. Now, as you can see, there's a cyclone outfitted. The feedstock comes in through that smaller line to the left of the yellow beam, into the cyclone, gets spun out, drops into the rotary airlocks, blended with nitrogen, and into the hot oil bath. The transport air is filtered and then exhausted through a couple the solids in the reactor get pulled into the fluid. Down below me you can see a blue motor with a yellow shaft, hazard protection, and a pump. That pump pumps the catalytic cracking fluid into this tube and shell reactor heat exchanger, making up for the heat loss of introducing feed. The warmed catalytic cracking fluid is then dispersed throughout the headspace of the reactor and onto the new feed. The solids crack, produce vaporous hydrocarbons and carbon monoxide, and they leave through this chamber here. This chamber is for collecting and returning aerosols to the reactor. It takes the place of a small bubble cap distillation column in the original layout shown in the 2007 video. The remaining vapor, very low aerosol content, is then ducted to the distillation column. There's 40 trays in the distillation column, sieve trays instead of bubble cap as sieve trays. The fumes that go into the distillation column fractionally condense throughout the column and then re-vaporize in each sieve tray. Now you can see a couple pipes coming down the distillation column here, one from just above that mezzanine platform and the next platform above. These are fractional cuts of the condensed hydrocarbons that we produce in the reactor, and they get cooled and pumped by the sequence of pumps below back to these tank farms. Overhead vapor includes condensable water, condensable hydrocarbon, and carbon monoxide. The condensables drain into this decanter tank here, where we separate bulk water from a very volatile naphtha-like fuel. The overhead vapor of the decanter then goes through the separation tower and finally over to vapor consumption, intended to be a turbine generator. In the 2007 original design to remove solids from the catalytic cracking fluid, we incorporated a filter press in the design. Later, with a little more operating experience, we discovered that the solids were so fine they were not going to build cake on a filter press. So we had to go to a centrifuge design and wanted to work with a centrifuge that could operate it at catalytic cracking fluid temperature of approximately 300 Celsius. So this machine is designed for that temperature. Standing here at the distillation column at the top, about 90 feet in the air next to the Columbia River. Here's the product tank farm, the building we build all the equipment in. There's the reactor with the square header, cooling water system, the evaporative cooler with the big fan, control room with a white roof. Feed system is just the other side of that. The demonstration trailer here with the raised